Let's take a look at this theorem. If A is a subset of B and B is a subset of C complement, then A intersects C is the empty set. Before we prove this, let me just draw a quick cartoon to see that this actually makes sense. So here's the universal set. Here's our set C, and so C complement is everything that's outside of C. Our assumption is that B is a subset of C complement, so C is out here, B is out here someplace. B is a subset of C complement, and also A is a subset of B. We're supposed to show that A intersects C is the empty set, that there's nothing common here. So based on the picture, that certainly looks reasonable that A intersects C is the empty set. Let's prove this. Proof. And the proof is going to be by contradiction. And that's going to be fairly typical for proofs that involve the empty set. Suppose that there is some element x that is an element of A intersects C. That means x is an element of A and x is an element of C. So therefore, x is an element of A. If it's an element of A and an element of C, then x is clearly an element of A. Since A is a subset of B, we conclude that okay, so x is an element of A, also A is a subset of B, so that means that x also is an element of B. Since B is a subset of C complement, we conclude that okay, so if x is an element of B and B is a subset of C complement, we conclude that x is in C complement, or that x is not an element of C. If x is an element of C complement, that means that x is not an element of C. This contradicts the assumption that x was an element of A intersects C. Because after all, if x is an element of A intersects C, which implies that x is an element of C. So if x is an element of A intersects C, then x is in A, which means x is in B, which means x is in C complement, which means x is in C complement. X is not in C. But if x is an element of A intersects C, then x has to be part of C. So x is not in C, and also x is in C, so that's a contradiction. Therefore, A intersects C has no elements, so that A intersects C is the empty set. And so that's the end of the proof.